This event was recorded July 21st, 2015 in Salt Lake City.
Cool. Thanks, Phil. So we're going to have about an hour and then lunch, which is, I'm sure, the reason why half of you guys came. And then I'm sure the other half came because we said the word drone. Who's in that second half? Drone, 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 drone. Yeah, nobody cares about 3D printing. So how can we trick people to come into a presentation on 3D printing? Make it about drones. All right, so this is part of the Roadshow event, which is, this is the third date on the Roadshow event. We started it last week in Seattle, and we hit Portland, and now here in Salt Lake. And it's going to continue on, and it's all based around this quadcopter project. The idea for the Roadshow started about 5 weeks ago now, and I spent 2 weeks trying to convince them to let me build something else, and I failed. So I was left with about 3 weeks to tackle this project that we're going to see here. I don't know a lot about drones. I have exactly 3 weeks experience on drones, so there's probably people in this room that have more experience and more knowledge than I do. But I think that's kind of a testament to how well the tools work for me, SOLIDWORKS and the printers and everything like that. So really, I wanted to teach people about printers and the process of printing and how the printers would affect my life as a designer or as an engineer. And the quadcopter is really just a vehicle to make that happen, right? It's what filled the seats, I guess. So if you're looking for an in-depth presentation on how to build a quadcopter, you're not going to find it. Yeah, I know. All right, but hey, I learned a little bit, and for those of you who are new to it, then I'll probably be able to teach you a couple things. So I started putting this presentation together, and I wanted to see who had already incorporated, these two technologies that are already immensely popular right now, the drones or quadcopters and 3D printing. And I came across this Kickstarter campaign from a company called Helico, but their Kickstarter campaign was around this drone called the AirDog. And you see Edgar, the founder of AirDog, he had a company, Helico, that really was 3 people that had this vision for a drone that could follow them while they are surfing, follow them and keep a steady camera on them. And that was their idea. And this 3-man team developed this prototype, printed it out of some of the same materials you see up here, painted it, created a video, put that up on Kickstarter. They asked for $200,000 in funding. And by the end of the campaign, they had $2 million in funding. And all of that was created or enabled through 3D printing, right? And the marketing around those 3D printed parts. In the video, they don't highlight the 3D printing. They don't even say it. Actually, they do talk about 3D printing in the video on Kickstarter. But this quote right here I thought was pretty telling, and it kind of confirmed that, yeah, I'm on the right path here as far as 3D printing being a tool in our toolbox, but a very powerful tool. So there's a few people with interest in quads. Anybody built a quad? One person. Awesome. I'm going to try to avoid any in-depth conversation with you because I'm going to feel inadequate. What about the printers? Who has a printer already? Or wow, okay. A few people have printers already. And for those of you who don't have printers, have you interacted with printed parts at all? Cool. Are you a little bit familiar with printing? Because this is like very not an introductory course. So I'm not going to go over the details of printing, but during the lunch hour, we're going to have the lab open, and I'll be over in there, and you guys can see the printers in action and ask all the questions that you want about those. I do cover some of the printing aspect in here. All right, so these two topics, printing and drones, they're both topics that are getting a lot of press in the news. Drones more than printing, unfortunately. Especially when you have people like tying handguns to drones. You guys see that this week? Holy crap. It's crazy. But they're both enabling technologies, and they're both technologies that have a large community around them. And this is sort of what we talked about beforehand, is those communities based around these technologies is what's driving the technology to progress and become better. And that's a key aspect to, I think, their future success. I think both of these technologies are going to touch our lives more and more as the years come by. And they definitely have a very symbiotic relationship. So how has 3D printing specifically grown over the past, 30 years? 85 is when you saw the first 3D printing patent granted. And the bulk of the market has been in the industrial side of 3D printing, which is the side that we represent at GoEngineer, being Stratasys dealers. And you can kind of see how machine sales have steadily grown and really skyrocketed in over the past 10 years, except for that little dip for the recession. But then I thought this was pretty interesting as well. These are people reporting the first time they've experienced 3D printing or first time they used 3D printing. And again, starting around 2005 is when you start to see a huge explosion there. And a lot of that's tied to that open source project, RepRap started in 2005. And the open source consumer grade machines have really driven interest, while the machine sales and the revenue has really been on the commercial side. Because what happens, I think, is a lot of people in here are probably tinkerers and do-it-yourselfers. And we personally buy a machine because we can afford a small machine now. And then we use it for things like injection molding small parts. And then we tell our bosses in our company that, hey, we can use this for more industrial uses. And that's really what's driving sales right now. Sales in pretty much every industry. Phil has interacted with people in probably almost every industry that you see up here. The big three, aerospace, automotive, and medical, those are where the bulk of our applications are. But it's becoming fascinating, some of the other industries we're involving ourselves in, naming like fashion and jewelry, because these are industries that me as an engineer never really envisioned myself interacting with. But with the printers, I am now. And those industries are just full of creative, crazy people that are using the printers in creative and crazy ways. And they're really progressing what we can do and what we're willing to try with the printers. And so when it gets into like casting, investment casting for jewelry and fashion, we probably wouldn't have tried that. So the applications that we're going to talk about, and the most popular applications that we see day to day for our printers, number one is still prototyping. 3D printing it was known as a rapid prototyping technology, and that's what it was called for the longest time. Probably not until the last 5 years where it became more 3D printing and now more additive manufacturing. That's going to be, probably 60% of the use today is still in prototyping. But where we're starting to see a lot more uses are in some manufacturing related uses. So supplementing already existing manufacturing technologies like urethane casting or injection molding or carbon fiber layup, making those processes more efficient and cheaper and more accessible through 3D printing. So I'm going to have some examples of those in the context of the drone. And then also marketing. I kind of talked about that with the AirDog example. These guys, three-man team, create a drone, a couple prototypes that are functional. They videotape it, they take pictures of it, they put those online, and they basically can show everybody, we have a product. It exists in this one small form. We want to make it bigger. Help us do that. But without having that functioning prototype and having a good video to go along with it, it's really hard to excite people about something that really doesn't exist yet, right? So we're starting to see people using the printed models in a lot of their marketing materials, online videos, handouts, brochures, bring in scaled up or scaled down models to trade shows to give out, something like that. Because you can create these immensely complicated shapes, and it's no hassle to manufacture those, right? So there's a lot of different ways to 3D print parts. And again, I'm not going to cover the basics, but at its most elemental level, 3D printing is just an additive manufacturing technology, right? You start from nothing, you build up layer by layer. Those layers are all sorts of different materials, plastics, metals, gypsum, waxes, all sorts of different types of materials. The two technologies that we deal with are FDM and PolyJet. And those are the two technologies that fall under that Stratasys umbrella. FDM uses thermoplastic materials. So up here, and I'll pass around some parts, we have parts made from ABS, ASA, which is like a similar to ABS, nylon, polycarbonate. There's a thermoplastic called Ultem, which some people may be familiar with. That's what that AirDog example was printed out of. It's an FAA certifiable material. It's really popular on the base. And then on the PolyJet side, everything is a UV cured resin. Because of that, we can get all sorts of different qualitative and quantitative differences in our materials. So we can have a wide range of colors, a wide range of flexibilities, clarities, stuff like that, at a very fine resolution, small surface feature. And I use the PolyJet technology for a lot of the molds that I did up here for some reasons that we'll talk about later on. If you guys are interested in metal printing, these are 3 technologies that you'd want to investigate. They use powdered metals with different power sources to create titanium, aluminum, tool steel, gold, silver, all sorts of different metal parts. So that's going to be the overview of the printing itself. The rest of it we're just going to talk about through the context of the photos that I show. So build a drone, like I mentioned to you guys, and a couple people came in late. I literally had 3 weeks to put this together. And I'm starting from knowing what a drone was, but not really knowing what it was inside, to having to build one. So I got online. Luckily, there's a very strong online community around building these. And I started to do some research, just like probably almost everybody in this room has been asked to take on a project that they feel like they have nothing to start with, right? They're starting on the lowest rung of the ladder. So I did what anybody else does. They start doing some research. And I figured out that there's basically 3 categories to a drone. You have the electronics, which are going to be all off-the-shelf components. Developing our own circuit boards and stuff like that is kind of outside the scope of this project. We have the hardware, or the actual physical parts, and that's going to be where printing really is most applicable. The creation of the chassis, the arms, the body panels, the overall design. Also, any assembly fixtures or test fixtures I might want to implement. That's where 3D printing is really going to come into play. And then once all of that comes together in this form here, then there's some programming, helping it fly and doing some further testing on it to sort of refine and iterate that design. So the workflow that I followed is basically that. I get online, I buy all the off-the-shelf components that I find, and then start the design. Hopefully get a design, prototype it as fast as I can, assemble it, hopefully it assembles. Once it's assembled, start doing some testing on it and iterate that process. And the faster I can work through these steps within a certain budget, and the more prototypes, the more cycles I can do through this within a certain budget, the better my project's going to end up. And that's where 3D printing makes the most sense. And like I said, this happened in a matter of weeks. This is my 3rd prototype, including all the design and everything within a matter of weeks. So that kind of gives you an idea of how fast-paced we're moving here. So the electronics, I included some of the electronics for people who had built a quad before. They might be interested in this. This is all based around the multi-Wii board, which runs off an Arduino. And the electronics include a lot of different sensors, flight controllers, motor drivers. These things are basically little flying robots. And if you have a sensor in mind, you could probably figure out a way to integrate it. This particular one has a GPS, a compass, a barometer, and then other drones will add like ultrasonic sensors, light sensors, and all sorts of stuff. You have the GPS here, the flight controller here. These are little motor drivers. The motors are kind of out of here, but they're little 220 watt motors. These things spin at about 10,000 RPM. It's crazy. If you haven't seen one in person, you'll understand why they call it a drone, because when you fire it up, it just drones. It sounds really cool. It's like a bee. All right, so these are after I did a lot of work extending the wires and whatnot. So now that I had all of the electronics, I had to come up with a design, and I'm not very good at drawing by hand. So this is about the extent of what I drew on the paper. I came up with a concept, and the first thing I asked myself is, what's the most important thing? And it said, it has to look good, right? So everything was based around this vision for what it looked like, which is basically our logo with a few motors around it and kind of a side profile that looked like that. That's what I started out with. You have to start with something, right? As soon as I got that far, I'm like, great, I'm going to go into SOLIDWORKS, which is where I much prefer to design in, because in SOLIDWORKS, I can say, this line is straight, and then it's straight. In paper, I can't do that. But very early on in the design process, I had to make a decision as to what direction this project was going to go. Here I am, I'm a designer, I have access to printers, I have a project. How am I going to utilize those printers that makes the most sense? Before I started designing anything, I have to come up with my storyline. Is this drone going to be something that I envision taking into mass production? Is it going to be something I'm building in the thousands or more, right? Because if it is, I need to design for manufacturing processes that can accommodate the creation of 1,000 of these, right? So I need to design for more conventional manufacturing. The arms, I better design them in a way that I can injection mold them, or the board and whatnot. Okay, so if I'd gone that route, I would have ended up with probably simpler parts on a one-to-one basis, and also probably more individual parts. Or I can say, you know what, this might be a one-off or only a few different iterations of this. It might be something that's totally custom. Am I going to use the printers in how they want to be used and create designs that I couldn't manufacture any other way? All right. So that's the route I chose because it's more fun. But you can kind of see these two images here. They tell the difference. You're immediately aware of the difference. The bracket on the left, it follows all your conventional rules. It's a cast part. It has holes that are accessible. It has wall thicknesses that are relatively uniform. It has these deep channels that are, have very wide radiuses on them. You could machine that and cast that no problem. The bracket on the right is designed for additive manufacturing. And if you were to want to machine this or cast this, it would become very difficult, if not impossible. They both do the same job. But the bracket on the right has been optimized because when we design parts, we essentially optimize to the point that we can manufacture them cost effectively, right? And all 3D printing does on an end use scale, which is what you see here, is it moves that threshold so we can optimize a little bit farther. So I went the design for additive route. Okay, so very early on, I realized I have a lot of empty road ahead of me, meaning this project was so open-ended, I could go almost any direction. And that's some advantages and disadvantages, right? It's great because I can be very creative and I can take it the way I want to go. But it also means that there's a lot of pitfalls that I could fall under, right? There's a lot of routes that I could take that end up not panning out. So very early on, I realized that I'm probably going to go through several different prototypes to find which one works well or works at all, or which one is appealing to people. So it started out as early on as this, just deciding how are my rotors, maybe I have 4 rotors, but how are they going to be oriented? And again, for this personal project, I chose what I felt looked the best, but also what I think would perform well. So I think I ended up going with something like this here, a little bit offset. And then we jump to something like this. So this is, 25, 30 hours later in SOLIDWORKS. And we got something like this. It's exactly how I pictured it, and it's exactly how I wanted it to look. And I didn't really have to make any concessions as to how I designed it based on the manufacturing method. Okay, there was some rules that I followed, but I didn't really have to make concessions. And hopefully, I'll be able to explain what I mean through some examples here. This is kind of how the back with the body panels looks. You can see all the components nestled in here. This is all just done up in SOLIDWORKS just to make sure everything fits correctly. What do you guys think of the design? Correct answer. All right, so here's the chassis. That's a single part. That's a complex part. Anybody in here involved in manufacturing? Cool. If I came to you and I said, here's the part that I want it made. I don't care how you make it. What would your answer be? Good answer. Say you're not familiar with 3D printing. I say, I want this made out of Delrin. Can't be done.
Have to cut it in half or something.
It would be several different pieces, right? At bare minimum, you'd have to piece it up. But I've designed it the exact way I want it, and I've got features in here that work intuitively because I designed them to work the way I want them to work. I have bosses in here that Velcro straps just come in and come out. Something like this, to have a strap come in and out, normally I'd have to put it down through the wall and I'd have to have a hole in the bottom floor. You know what I mean? Because that's the easiest way to manufacture that. But now all of a sudden I can get debris and stuff inside them. So that's not what I wanted. Everything is designed exactly how I want it. Here's another example of just the arm itself. These arms, the rear arms are symmetrical, so I can swap them. The front arms are not. Again, with printing, there's no downside to have asymmetric parts. You know, it's one extra part that I have to keep track of, but in terms of manufacturing, there's no additional cost or additional overhead in manufacturing two parts that are mirror opposite of each other. There's one difference there. The internals of this, it's been, well, I should say I started out with the shape of it. I put the motor where I wanted it, and I put the body where I wanted it, and then I connected it. So it ends up with this downward slope. It's got sort of this airfoil shape to it. The inside is hollowed out, and it's got about a 1/8 inch wall all around, which means it creates this cavity that would be trapped under normal circumstances. If I was going to cast this, which I eventually did, cast this out of urethane, if I were to cast this as is, I would not be able to remove whatever core I had in there because of the shape of that. Right, so it's been optimized up to the point of manufacturability. I'll talk about more how I did this when we get there. It's been designed to take threaded inserts. You guys might be able to see that up here, and when you come up and look at these parts. And actually, I'll just pass one of these around. It's got these brass inserts. Those are heat staked or really just pressed in with a soldering iron. You create a tapered hole, and I just have a library feature inside SOLIDWORKS. Has a tapered hole. I just pop it wherever needed. It's like an interference fit. So the brass insert, as you heat it up, actually melts the plastic around it, presses in, and then when it cools, it's in there very solidly. That's great. I can design around that if I'm going to be printing in thermoplastics, but now if I want to print in one of the polyjet materials, I have to change how I do those threaded inserts because the rules are a little bit different depending on your method of printing. So even though we have more design freedom, each technology that you use to print kind of has its own quirks. One of the quirks here is that these are thermoset, so as you heat them up, they're not going to soften like those will and take that insert. All right, so the first prototype. At this point, we were having our kids camp here, and all of our machines were, or all of our FDM machines were really full printing these kids camp parts. And so I need to get rolling. And I thought, well, I'll start on the wiring because all these motors just came with very short leads. I had to do all the wiring. So I said, I'll print a partial prototype. I cut away all the most complex materials, things that would require a lot of support material. And I printed this guy very quick. And it's about a 4-hour print to give you guys time scale. But this I called my wiring jig because I was able to hook up all the electronics and do my wiring harness before I would normally have been able to do it. This was actually the very first part I printed. I wanted to make sure that the motor could pop in there, which it did. And then I had to handle all the connections. And you've used these bullet connectors, right? Anybody else use bullet connectors? They're little guys, and you have to fill them with solder. They can be kind of a pain, right, if you don't have a third hand or something helping you. So what I created was this little soldering station. These things have cavities in them, and you have to completely fill them with solder. So you have to heat them up and just fill that cavity with the solder. So I made this little soldering station with some work instructions so I can give this to people in our other offices and they know what to do. It's printed on the polyjet. It's fairly small. It's only about 1 inch. And it has this rubber-like material on it to keep it from sliding around on my desk. I work in an office. I'm a manufacturer and I'm in my cubicle, right? And so there's certain things that I have available to me and certain things that I don't. But I basically work on a wooden desk. That's nicer than it should be. So anyway, it's slick. But with this rubber-like material, it doesn't slide. It's kind of cool. But think about this in the context of like an assembly line or something more industrial. All of this is applicable. I have work instructions in there. I have some features in there that I wouldn't have been able to do because they're not cost-effective otherwise. This guy's small, but it printed in about 20 minutes. So it took me longer, I think, to design it. And there's the wiring and everything. You know, I had to figure out how long these need to go, etc. This did the job for what I needed it to do, which was wiring, but it didn't tell the whole story because it wasn't a full prototype. So as soon as the machines became available, I started printing this guy up, which was my first prototype. I did it out of FDM. The reason why I wanted FDM is because in the internals here, where I don't have a thin wall, I can actually tell it to print sparsely on the interior. So even though my wall might be a 1/2 inch thick in some areas, the inside is still mostly air. I can't do that on polyjet. That's about a 20-hour print. So to give you an idea of the timeline here, and as I'm working, I'm always thinking about how long these prints are going to go because I want to keep the machine running constantly. So for something like that's 20 hours, I'll try to start it a little bit before the end of the day so that it will finish around lunchtime the next day. And then I might be able to get another short print in before the end of the day and then do another overnight print. So I'm basically building as many parts to get me to the next point that I'm going to be in the office or ready for parts. That's one thing that's very different than calling up vendors and asking how long is this going to take and how quickly can you rush it. So first full prototype. Now that I have a prototype, I got to start assembling it. How many times have you guys been in a situation where you start to put pieces together and holes don't line up? That's SOLIDWORKS' fault. I have screenshots to prove it's SOLIDWORKS' fault. But I still have to fix it, right? I can't.
Reference fault.
You know what? Have you guys used SOLIDWORKS? I use convert entities on this. It's supposed to project that, but it projected and shifted it. I don't know why, but it did it. To be honest, I had printed probably 8 or 9 arms by this point, but I had never plugged it in, and I had never tried to put a screw in there. So until I did that, I had no idea, right? But it's very easy for these design flaws to kind of slip past you, and the longer it takes to identify them, the more expensive those mistakes are. If we can catch it early on, and we catch it early on by going through a lot of prototypes, the better it is. A couple other things that didn't work out right, some features that were a little bit too small, and this was a game, this just stopped everything. I couldn't fit the battery in. That's the battery, it's supposed to slide in there, and it doesn't. So that one's my fault. But that's one of those things where as you're designing, you're trying to picture how is this going to come together? And you kind of have an idea, and there's situations where it's close, and you have to make a decision. Am I going to spend 2 hours ensuring that it's going to slip in by adding more features and whatnot? Or do I know that in my budget, I have time and money for a certain number of prototypes? I'll just let it slide, and if it works, great. If it doesn't, then I'll deal with it, especially if you're on a short timeline. I tried as hard as I could to get that in there to the point where I dented this guy, and I'm not going to use it any longer because I don't think it's safe. But I changed the design. It didn't work. Learning from my mistake with just the little partial prototype, I did everything I could with this just to make sure I came up with every design change that I wanted. I think I came up with 8 or 9 different design changes. But the thing never got put together because it didn't work. So what I did is I ended up putting a little recess down here in the bottom so I can actually pop the battery down, then pull it up and slide it in. That makes sense. Increase the thickness of some bosses, increase some sign zip type features, added some clearances for some certain parts that I thought would squeeze more than they did, and fixed the SOLIDWORKS error there. And then I start with the next thing. So, it took me probably a day to put this together, figure out what I wanted to change, make those changes, and then I start to print before I leave work that day. Okay? And now what you're seeing there is basically this revision here. And it's all printed up. It's got all the support material around it and whatnot. So as that guy was printing, I started asking myself, what else can I do to, 1, make this roadshow more interesting, but 2, make my quadcopter more interesting and more complete. I wanted to move away from some of the 3D printed components because I felt like I was sacrificing some strength and rigidity in some of these components. So I thought maybe I could urethane cast some arms. So instead of using 3D printed arms, can I 3D print a mold and do a urethane casting of some arms? Urethane's great because I can get urethane in all sorts of different varieties with different strengths, filled with all sorts of different materials. And I know I can create an arm that has thinner walls and is more rigid than a printed arm. So that's what I wanted to do, but I'm still using printing to make that possible. Because printing is great at creating complex shapes, and it's great at creating those accurately. So I printed these, first I designed this. Now remember, these arms were designed in such a way that it would create a trap core. So I actually had to change the inside geometry of this arm to allow me to create a core that would slide out. And I sacrificed some things for that because now, all of a sudden, the walls in this, especially on the bottom as this tapers down, become really thick. So it's not quite what I wanted, but I have some plans to change that. I'll touch on in a second here. But that's a complex mold, right? That's, what, 7 pieces that have to come together in just the right way. Designing that is not hard. I mean, it takes some SOLIDWORKS skills to design that, but the design part's the easy part. You know, manufacturing the mold, I think most people would agree that that's going to be the challenging part, especially if you don't have a printer, right? But we do have a printer, and we can create that right here in our office. So that's what that looks like there. Now, my original idea was I wanted to do like a vacuum infusion on this, which would mean these barb fittings connect on each side of this, and I wanted to connect this to my vacuum pump, pull a vacuum on it, and then just use the vacuum to infuse the resin. Well, it didn't work because I couldn't pull a vacuum on this. It just didn't seal as well as I thought it would. So I just ended up using a syringe and just pushing this resin in. This is a tooling resin. It's a filled tooling resin. It's quite stiff. The design of these barbs was kind of neat. I was thinking that I'd have a line in, a line out, and the resin would stay in those lines and cure. And I was worried about, I wanted to use this more times, because one of the great things about urethane casting is for one mold, I could pull dozens of parts pretty quickly, right? This stuff has a pot life of 6 minutes. So I can do this stuff pretty quickly. So I wanted these to be able to pop off. So I made these separate parts, and I did, again, that soft material there, and I made an interference fit on there. So these actually press in and would seal. Does that make sense? So there's sort of another design that has extra features built into it because it's printed. Just use standard 1/4 inch bolts, bolt that thing together, you end up with something like this. Now I did this late at night, which means I didn't cure it under pressure because I couldn't turn my compressor on because my neighbors hate me already. Didn't turn my compressor on at 2 in the morning. So normally you'd want to cure this at about under 40, 50 PSI pressure. This was cured under just ambient pressure. But I did vacuum degas the resin, which is important. So this isn't the best that we can do, but it's still pretty good. There's some bubbles in there. You notice it is heavier, and that is because I had to make some sacrifices. What I'm going to do next time, as soon as I get a chance, is instead of having that core that slides out, I'm going to print in our soluble FDM material. We have material that will just melt away in water. I'm going to print a core out of that material, cast around it, and then pop that whole part in our bath, and the core will just melt away. And then I can end up with a very thin wall. It's going to be exactly what I want. Just another unique usage of that printing technology. That's something that we use already in carbon fiber layup. All right, the next thing I want to do was some injection molding. We have this little injection mold press. Some of you guys may have already seen some of this. We use this press all the time here now. I wanted to change the storyline a little bit. You know, I'm pretending that I'm creating this consumer product really based around the drone, and I bought off-the-shelf propellers. But what if instead I want to design my own propellers? That's my business, is designing propellers. There's easily 1,000 different iterations I could make of this. Different materials, different pitches, different lengths, etc. How do I get good results, good testing on something like that? Well, I have to make prototypes and I have to functionally test them. With these materials, this is polypropylene, but these actual ones are some sort of filled polymer. You can machine those, but the machining can be complex. It's 4-axis machining, and it can be time-consuming to program each and every single one of those. Whereas I could pop in and design different molds. I could design 5 different molds using a design table inside SOLIDWORKS. I could save them all out, print them all at the same time, do 5 iterations at once, for example. But when it comes to materials, we have a lot more materials available to us in injection molding, right? We have polypropylene, polyethylene, Delrin, nylon, filled polymers, all sorts of stuff that we can do. This image that you see here is, it's a 3D printed insert. This is intended for short run stuff. So I made 2 of these so far. My mold's in good condition. I'll probably be able to create a dozen, 2 dozen more, no problem. But I'm not going to be shooting 1,000 parts through here, right? These guys here, they're doing polycarbonate medical device parts, and they're aiming for 50 parts. And in this particular situation, they need 50 parts for FDA certification testing. But if you're evaluating an injection molded part for your design, it's normally pretty important that your prototype is injection molded. the material properties from a machine polymer versus an injection molded polymer is actually different. The design, nothing too special about that guy. I also printed this on the PolyJet. The reason why I'm printing these on the PolyJet is because I can take these off the machine and use them without actually doing any hand finishing. No sanding, no deburring, nothing. And that's critical because as soon as I take a piece of sandpaper to this, I round that edge, I'm going to get flashing all around that part. That part that you guys are passing around has absolutely no trimming done to it. Just a close-up there, but you guys have the part. Last thing I wanted to do was some composites. A lot of drones are made out of carbon fiber because it's lightweight, it's stiff, and you know, I wanted to integrate some carbon fiber to mine as well, especially once I put this thing together and I realized that it's a pig. The thing weighs, it's a lot. It's probably 5 or 6 pounds. We use 3D printed carbon fiber layup tools and cores pretty often. We have materials that can withstand the curing process of the carbon fiber, either in an autoclave or out of autoclave. And just depending on the temperature requirements, we have different materials available. But the process is the same as just a standard carbon fiber layup, but for the most intense or most difficult parts, creation of the layup tool, we use printing. That's basically what we're getting here. So this is a layup tool. It's just standard ABS. This is the part I want to create. These parts have some standoffs you can see under there. So I made these inserts. These are meant to be inserted down after I have a couple layers of carbon. Those inserts popped in and then more carbon laid over top of it. And then a nice little trim guide. So once it's been cured, I can trim it to size. Again, this example is relatively simple, but the end use practicality of something like this, trim guide that could be fairly complex in shape, is real. And we have people buying machines exclusively for that, trim guides and drill guides. If you noticed, a lot of these pictures, they all have this really dirty table that they're sitting on. These are all done in my garage, which means all of this is very approachable. It can be done in an R&D setting. It can be done at home. I'm not showing you guys anything that's going to take more than $1,000 worth of equipment and a couple hours Google searching. This is amateur stuff. Everything else was printed here in the office. You know, you look around, this doesn't look like a manufacturing firm, right? And our customers are becoming manufacturers despite having downtown office high-rise locations. This is a wet layup, meaning my fiber matting was dry, and then I mixed the resin, basically painted on. That's the alternative is what's called pre-preg. And pre-preg would have a mat that already has some resin infused into it, and you just have to bake it, and it activates the resin. That usually looks a little better, but I haven't sealed my oven yet, so I just use vacuum bag, which works pretty well. And there it is after it's cured, and then I pop the trim guide on it, and I'll pass this guy around. That's the top panel for this quad, and I plan on replacing the other panels with some carbon fiber parts as well. So as I mentioned, this is a roadshow, and it's following a project that is continuing, you know, as we do more of these. What's next for me? Some people asked if this flies yet. It would fly very well if it weighed less. I'm going to get some bigger propellers. There's some things I want to do to help it fly and get comfortable flying it. Because once I have it flying, then I can do some more functional testing. Part of that process is going to be lightening it up a bit. So I think having some cast arms that are thinner, but still a rigid material is going to help a lot. Also, taking better advantage of being able to make a sparse fill part, because I showed you it has some very thick walls in certain sections. And I'm using basically not the most sparse fill, because I was kind of concerned about the strength of it, but now I'm more concerned about the weight. So I'm going to change that a little bit. Notice none of these are really design changes yet, because there's still some flexibility in the printing parameters that I can do. But it's probably going to need some design changes as well. There's also some other things as far as like topology optimization. So this example here, the creation of this shape is not really arbitrary. It's done through a computer. It's done through an FEA analysis that says, okay, start with this shape and put these loads and constraints on it and reduce the volume iteratively until you get to a point where you're no longer at your desired factor of safety, right? And you can end up with something like this. So I'm going to probably investigate doing some of that, maybe with the arms again or some chassis components and kind of whittling it down. And then also add functionality, because the nice thing about having a printed project is I'm not invested in the tooling for any of it. So I could continually upgrade and add things, and as I get feedback or people saying, hey, you should add a camera gimbal, or you should add a poison dart gun, which was a real thing that somebody suggested. I can assess those, and I can choose to pursue those or not, because I'm not heavily invested in the design. I'm emotionally invested in it, but I'm not monetarily invested in it. So that's pretty much the presentation. I wanted to give you guys a glimpse into what it's like to have a printer on site and how it changes some of your design decisions and how the workflow is a little bit different.